Jai Hind everyone. I am Anupam Kumar Saini, IT Department, AKGEC, Ghaziabad. Today I discuss topic Hamiltonian graph. That is important topic of discrete mathematics of second year student. This topic is important for CSE, CSIT and IT student of second year. Here today I discuss the graph Hamiltonian graph. Hamiltonian graph are that graph in which all the vertices should traverse without repeating of any vertex except initial vertex. Here the definition: a cycle in a graph G is said to be Hamiltonian cycle if every vertex except for the starting and ending vertex in V is visited exactly once. A graph is Hamiltonian or said to be Hamiltonian graph if it contains a Hamiltonian cycle. Here we take a graph ABCD, A, B, C, D, a graph in which there are edges 1, 2, 3, 4 and 5 are the edges. If we take any graph in which all vertex should traverse, then the graph form Hamiltonian cycle if start and end vertex will same. Here vertex start with vertex A, then go with D, then C, B and A. Means start and end both points are same, then form Eulerian cycle. Hamiltonian cycle. If a graph start and end point are same, then it will form Hamiltonian cycle. Here we see that A, B, C, D, then A, then Hamiltonian cycle will form. We take another example. We go with another example of a graph in which vertex A, B, C, D, E, F, G, H. These are the vertices. These are the vertices. This is a graph in which we find Hamiltonian graph. We start with vertex A, next vertex F, E, D, C, H, G, B and A. Here start and end vertex are same. Then we obtain a graph like this, in which all the vertices with traverse A, B, C, D, E, F, G, H. Each vertex has traverse in this graph. without repeating of any vertex except initial vertex. Then the graph will form Hamiltonian circuit or Hamiltonian cycle. This is another example. Vertex A, B, C, D, E. This graph is not Hamiltonian. We see that if we traverse this, go with B, C, D, E. All vertices are traversed, but start and end point are not same. Then Hamiltonian cycle will not form here in this graph. Then this graph is not Hamiltonian graph. As we see in previous topic, Euler circuit, Eulerian graph, we obtain the Euler graph with a particular method. The solution of obtaining by Eulerian graph is graph coloring method. With the help of graph coloring method, we can find out the given graph is Euler graph or not. So our next topic is graph coloring, that is solution of, we can say that is solution of Euler graph. Graph coloring, let G be a graph and C be a set of colors. Graph coloring find assignment of color of different nodes of G so that no two adjacent nodes have the same color. In other words, we can say that if any graph, there is a graph A, B, C, D. This is a graph A, B, C, D. We assign color to each vertex and each vertex with different color in such a manner there no two adjacent vertex have same color. Two adjacent nodes have the same color, means if a node A we put color with red, then adjacent vertex of A is C and B, we cannot put red color to B and C. Then we have to put new color to C and B, we give it to yellow. Adjacent of vertex C, adjacent vertex of vertex C is vertex D, then we cannot put the same color yellow to this color, this node D, and adjacent of C is B, then we cannot put yellow color to vertex B, means vertex B is adjacent to A and vertex C then yellow and red color cannot be assigned to vertex B. We have go with other color. We assign it blue, means now vertex A is red, vertex B blue, and vertex C yellow. We see here the vertex D, we cannot assign it color blue because adjacent of B. We cannot put color yellow because vertex D is adjacent to vertex C. But vertex A is not adjacent to vertex D, then we can put red color to vertex D. If we add one edge between A and D, then vertex D will also be adjacent to vertex A. Then in this case, we cannot assign red color to this node. We go with another color. Means if we can say that a complete graph have colored with n colors, means this is a complete graph of 3 vertices, each vertex connected with other vertex, then every vertex have different color, red, green, yellow. Complete graph of K4, we see here the 4 different color. If we take simple graph of 5 vertex, we take this graph only, this is not a complete graph, this is a graph of 5 in which there are 5 vertices. We assign color this graph red, green, this is adjust vertex A, B, C, D, E. We assign red color to A and G, green to B because both are adjacent. Vertex E is not adjacent to B, then we can put here G, green. We modify this graph. Now if we assign a color green to this graph, then this vertex, if we assign G to C, then G is vertex B is adjacent to vertex C, then we cannot put the same color with this graph. And vertex C is adjacent to vertex E also that have green color, then we cannot put green here, but we assign red color because vertex A is not adjacent to vertex C. If we add this vertex between A and C, then vertex A and C will be adjacent, then we cannot put the same color R. If this vertex is not here, then we can put the red color. Here we assign white in this case. Now this vertex is adjacent to C, D. This vertex C is adjacent to D and adjacent to E and adjacent to B, then and adjacent to A. This vertex is connected to all remaining vertices, then these colors we cannot put here. We assign new color here to this graph. Minimum number of color to color any graph is known as chromatic number of the graph. Here we can say that the smallest number of graph of color needs to color a graph is called its chromatic number. Then chromatic number of this graph is 3 and chromatic number of this graph is 4. If we take this graph, A, B, C, D, we go with yellow color at this vertex, white because this vertex is adjacent to this vertex is not adjacent to A, this is A, B, then we have put the same color, we can put the same color yellow, and this vertex D is not adjacent to B, then white can be assigned. Then this graph can be colored with exactly 2 colors. Then the chromatic number of this graph is 2. As I said previous that to find out the graph, given graph is Euler or not, we can add this phenomena in that graph. For example, if we find out this graph is bipartite or not, if we color this graph, if there are exactly 2 colors are required to color this graph, then this graph will be Euler graph. Here we put red, white, red, white, but this vertex is adjacent to this vertex and this vertex. Vertex A is adjacent to vertex B and C. Then we cannot assign the same color that is already given to B and C. Then we have to give new color green to A. Then this graph will not color with 2 color. Then this graph will not be Eulerian graph. As we see here, this graph is colored with 2 colors. This graph is colored with 2 colors. Then the graph will be Eulerian graph. We take another example. What is chromatic number of these 2 graphs? Here are the 2 questions in which find out the chromatic number of the graph. Vertex A, B, C, D, E, F, G. Graph G, we put a color A, red, green, yellow. Means these vertices are, each vertex A, B, C are adjacent to each other, then we cannot put the same color. Then vertex D is not adjacent to A, then we put red here. This vertex is adjacent to G but not C, then yellow can be assigned here and green can be assigned here. Now red, this vertex not adjacent to this and this, then red will assign here. Then the chromatic number of this graph will be 3. We can color with 3 colors. If we say that this graph will be Euler graph or not, then the answer will be no, because this chromatic number of this graph is 3. For Eulerian, for bipartite graph, there will be exactly 2 colors are there to color a graph. Then the graph is bipartite graph. Now find out the chromatic number of this graph. AB, if we assigned red here, yellow, green, red here, yellow can be put here, and this will be red, green, yellow. If we assign red here, then green, this go with green, and yellow, this is G, this is G. Yellow means green, yellow, red, green, red, and this can assign with red. Means chromatic number of this graph also 3. Okay, this is graph coloring, in which all the vertices are colored with the different colors, in which no 2 adjacent vertex will same color. This is the topic of DSTL. Okay, thank you.